person nodding. Oh, another thumbs up, okay. Please take advantage of the office hours. We appear to have excess office hours so far. TAs have lots of time to talk to people. They're both on Ed and have Zoom office hours. All right. I want to finish off the example we did last time. Most of the lecture is going to be about lambda, map, and filter. These are not, in a sense, very difficult concepts. You look at what lambda is, what map and filter do. Very short definitions of map and filter. It's more the methodology involved in using it. It's a different way of trying to solve problems. We've been focusing on recursion so far, but that's just one part of functional programming. There are other ways of thinking about problems that don't involve recursion. Recursion is, in a sense, it's kind of like loops. It's something you do at the bottom of the level to deal with the details of the data structure. But often you can abstract away from that a little bit and piece together things you've already implemented to do what you want. And things like map and filter are great tools for that. You've seen both of those in Python, or maybe you've seen them. They're pretty well used there, but they only work for a few particular data types that are built into Haskell. In this functional setting, map and filter and things very much like them are really a kind of a core way of writing more sophisticated programs. So it's a different way of thinking about things. Writing things in terms of recursion and then these higher order constructs. And by higher order, I mean things that take functions as arguments. You're not so used to that, I think, from previous programming. Most languages, including Java now, allow you to take functions as arguments. Even C lets you take function pointers. But it's not a style of programming that you rely on. It's not one of the core methods you use to solve problems. Here it is, and we're going to see some examples of that. Lambda, map, and filter are just a starting point. The first examples that we'll see a big class of things that are quite useful. All right. I'm using yet another approach to getting both screens showing here. All right. I want to try and quickly do this example from last time. So this is not a map and filter example. This is just more on using basic kinds of recursion with pattern matching. A slightly more realistic example that we've seen before. Defined what the problem was. So remember we have this class of arithmetic expressions. And the expressions are either a variable, which is a single character, or negation of an expression, or a plus of two expressions. And to make them easy to parse, we're putting parens around everything. So you go minus with this one argument, that one argument has to have parens around it. Plus of two arguments, those two arguments have to have parens around them. And the only thing it doesn't have parens around is just a variable, a single letter. That makes things a lot easier for us. You can see I wrote this pretty printing function which just takes an expression represented structurally with the constructors, var, neg, and plus, and turns it into a big string. And we saw an example of that last time. And parse is just supposed to be the inverse of that. You can see from the structure that this pretty printing thing here, it's doing what I said, right? You look at the plus, for example, here. You can see the two recursive calls. So we have this, get off. Control Z doesn't work. Okay. You can see the two recursive calls there, PPV1 and E2. Those give us the strings that we're assuming we computed for the two arguments. And now to make a string for the whole expression, we just put those two things in parentheses. got you can see the two expressions put in parentheses, and what should be in the middle here is, so these are, this here is the, it shows up here. Is it showing up? Oh, it is, okay. All right, so that's one of the recursive calls, and you can see that we're putting, oh, what is right? Okay, I got mixed up with the quotes here. These are the quotes. What we're doing is the plus appends a bunch of strings together. So this is a string here, and this is a string. It looks a little confusing because of the parens in it. And then we've got these recursive calls here. And so we're putting a left paren, and then a right plus left in between the two, and then a right paren to close it all off. So all we want to do then is take a string that has been generated this way, or if you're just writing it by hand, it has to be something that could be generated that way, and turn it into one of these expressions. Let's take a look at that. Do I want to save it? All right. All right, so let me bring up the file. All right, so here's what we did last time. Here's the definition of the data type I showed you in the slide. Here's the definition of the preprinter. Parse we got to start on. What we're doing here with parse is just following the standard recursion pattern, but we're refining that pattern bit by putting in some subcases. So the standard recursion pattern would say, well, string is actually a list of characters. It's important to remember here that a string is actually not a real type, it's just a name, an alias that the compiler eliminates as soon as it sees it. It turns it into a list of characters. So we're taking an input, which is a list of characters, and the natural recursion pattern is to look at the empty list or look at the case where it's one element followed by some other ones. But we're doing an additional case analysis on what that first element might be, because that will change what we do. And it's very handy to write that out in this pattern matching construct. And all of the cases will actually be quite small, and it allows you to see the structure of the program, the case analysis, directly looking at the definition. All right? So if it's a single character which is a letter, right? You just say, well, it's a variable. It's all written. It's all it could possibly be. So we'll just wrap that variable constructor around it. If it's any other character by itself, that's not an expression. Plus by itself is not an expression. It has to have arguments. So it has to be an error. Oh, except for, not quite, because spaces we want to ignore. You can put, even though the preprinter doesn't generate any spaces, maybe we'll relax things a bit. So if you're writing out yourself, you put in some spaces and they don't matter. But if we're going to do that, it means it should go before the error. Right? Otherwise, this third clause, which is now the third clause here, C could be a space and then we generate an error message. So check for space first. And if it's just a space, then we just, the same, the result of parsing space something is the same as parsing something. Just ignoring the space. And what else do we have to look at? So what are the other possibilities? What are the possibilities now for the case where it's a character followed by some string of characters? So now we've got something that's longer than one, and you've got a first character. So what are the possibilities there for a string? Well, we're trying to break it up into one of these expressions. It has to be one of these three expressions. If it's a variable, the whole thing's a variable, we've already taken care of that. What else can it be? It has to either be a negation or a plus. If it's negation, right, negation has to be the minus sign followed by something in parens. And if it's a plus, it has to be two arguments in paren. So the very first thing there is going to be the beginning of the first argument, which has to have a paren around it. So there's just two possibilities here. One is that the first character is a minus, or it's a left paren. All right, so let's consider the case where it's a left paren here. So let's put in the left paren character. So now this whole expression is left paren followed by a bunch of stuff. What it has to be in order for this to be a real expression, I didn't follow what I said. It has to be either a minus sign or a left. Okay, we actually did. Let me actually do the simpler case first. We'll postpone that, the case where it's the left paren. The other case I said was it would be a minus sign. It's the beginning of a negation expression. So let's do that one first, just because it's simpler and it involves creating a function. We'll move to the second part. All right, so it's a negative sign followed by a bunch of characters. Well, if the negation, it has a negative sign followed by something in parens. So that means what we need to do is we need to take that expression in parens and get the expression out of it, which basically involves taking off the parens and then parsing what's inside. So that's going to come up with plus, so why don't we just make a function out of that, a separate function, which we'll define below. So parse, we'll maybe call it parse parens. And we'll give it the whole expression. There's a way of getting this with a name. It's a little bit ugly, but I'm just going to do it directly here. So it's a little odd because I need to put this thing back together. What we want to do is call it on the list we were given, which is negation stuck onto these C's here. You can also put in, if you wanted to, you could put in str here. You put in another name with an @ sign. And what that does is when it matches, it does what you expect for the right part here. If it matches, it says CS is the remainder after the minus sign. But it also sets str to be the whole thing. And then we could just refer to it here. We can say parse print is that whole thing. To me, that kind of clutters things up. And your compiler will take care of this extra cons here. All right, so that's all we need to do in this case. It's just a paren thing. We parse it, and that'll give us the expression. That's the argument to negation. And now we need to make the negation expression out of that. And we can use the negation constructor for that. So that's all there is to that case. One thing that's it takes a little getting used to in general, but if you've ever done any programming in Scheme, it's even worse. There could be a lot of parentheses. Every time you apply a function to an argument, if that argument has multiple things in, you got to put parentheses around it. It's nice to avoid parentheses, and you get a nice syntax in Haskell for doing exactly that. We could write this here as negation, and then put a $sign. And what that means is that everything follows should be thought of as wrapped in parentheses. That's the argument. And so we can do this instead. Right, so you don't have to use that if you don't want to, but it is quite a handy thing, and it does help get rid of a lot of parens. So again, what you see something and then a $sign, it means that everything that comes after the $sign is the argument. It's as if you wrap it in parentheses. It's just you can view it as just a bit of surface syntax. Not really adding anything new to the language. All right, so that takes care of the negation case. So the only thing left is the plus case. And this, often parsing expressions for real language that involve operators, especially infix operators, plus and times. That can be a real problem. You have to deal with operator precedence, how you group things, you see plus and times together. But we don't care about that because we forced the user to write parens everywhere. All we really need to do in this case, if it starts with left paren, it has to be a plus. So what does that look like? It looks like, left paren, a string for some expression, right paren plus left paren something right paren. That's the structure at the top level. So all we need to do is to break it up into the two arguments. And to do that, we just need to look for the plus sign. But we have to be careful looking for the plus sign because the first argument could have deep inside it some other pluses. But that will be inside the parentheses. So what we'll do is we'll look across the string for the plus sign, keeping track of how many parentheses we've gone through without closing. Right? So if you see a left paren and you go inside that, now you've got one left paren that you've gone by, and when you see the right paren, then that closes it, and you can go back up a level. So we're going to keep track of the levels of nesting of parentheses that you're inside. And that's what we're going to have a function then that just looks for the plus, and it's going to be given a nesting level, and what you're looking for is a plus in the string that's at nesting level 0. So we'll call that find plus sign, and we'll give it again this whole string here, plus, and we'll just copy it here. So let's assume we have that. We'll write it in a second. It's an easy thing to write. So we've got this plus then in the string. At some point in the string position n, that's the plus that separates the two arguments. So what are the two arguments? Well, it's the string starting at the beginning, up to right before that position, and then it's the string after that position and onwards. And so this is an opportunity to introduce two functions here. I'm not sure if they're in the assignment or not, but functions that you use quite frequently for list hacking. You might have seen them in Python as well. That's take and drop. Here, let me show you the types here. All right, CI and type. So the two functions are take and while. Take and drop. They both have the same type. They both take an integer, and take takes the first, if you give an integer n, it takes the first n elements of the list and returns that. Drop does an analogous thing. It drops the first n elements and gives you the remainder. There's a handy way of getting chunks of lists, but it's ideally suited for this application here, right? What we want to do is make recursive calls on these smaller arguments. We need to get those arguments, and we need to put them back together with the plus constructor. That's what we're going to be returning here. So we know it's going to start with the plus constructor, and now we have these two arguments, which need to be expressions that we get from the two substrings of the big string corresponding to the arguments. Right. So what do those look like? Yep.
I don't understand the parse, parents, and find plus are functions.
Yeah, I'm going to define them in a bit. Actually, you know what? Why don't we just do it now? Otherwise, I could forget, and it might help understand this that if you do exactly what they did. All right, so let's look at parse parens. And good and. I always put the type in. You don't strictly have to put the type in. It's not just for documentation. It actually gets errors out. Often you know exactly what the type should be, and if your function doesn't actually have that type when it infers the type for it, then you've made a mistake. So it's actually a good debugging tool to always put the type in. I sometimes get lazy, and then half the time I pay for it. It's a ridiculous bug. Okay, parse parens, what's it doing? It's just taking a string and producing an expression. The idea is that there should be a string with a paren on one end, paren on the other end, and inside an expression it can parse. So let's write this here again. Is this another one of these standard? Actually, in this case it's not a standard recursion because we already have some tools that let us avoid recursion. So it's not that recursion is bad, but recursion is kind of a more operational thing, like doing the loops. You're going through something, so you need to understand the process of going through things, or in the case of recursion, you need to understand, what's the recursion hypothesis here. If you can just piece it together with some functions without recursion, then usually it's a higher level view of it. And in this case here, what do we want to do?